All right. Hello, everyone. Thank you for joining us today for our ALS Webinar Wednesday series. My name is Alex Yao. I'm the marketing coordinator for ALS North America, and I'll be facilitating the webinar today. A few helpful notes before we begin. If you're having technical issues with our webinar platform or any questions, you can type your message or question using the chat function at the bottom of the screen. You can also select the hand icon to notify me of your status so I can assist you. All questions regarding the webinar material will be answered at the end of our presentation. Our presenter today is Richard Chong. Richard graduated in the spring of 2009 from the University of British Columbia with a Bachelor's of Science majoring in chemistry. Richard has been with ALS for 11 years, starting in the fall of 2009 as a lab assistant in the Trace Metals Department, preparing samples for analysis, eventually becoming an ICPOES and ICPMS analyst in 2010. In 2014, Richard became a technical specialist for the Vancouver Lab, where he has developed many new methods and method optimizations for the Trace Metals Department. Richard also works closely with the national technical team to develop new ICPMS methods to be implemented across the Canadian Environmental Network. Last year, in 2020, Richard became a registered professional chemist with the Association of Chemical Professionals, sorry, with the Association of the Chemical Profession of British Columbia. Today, Richard will be discussing ultra-trace metals analysis in waters by triple quad ICPMS. Thanks for taking the time to deliver this presentation, Richard. I'll turn it over to you now.
Okay, thank you, Alex. Good morning, everybody, or afternoon, wherever you are. So today we'll be talking about the triple quad and how it can be used for waters analysis and environmental testing. And we'll go over a couple of specific applications that the triple quad was uniquely designed to, and then a couple other different challenges that face ultra-trace metals analysis. And then we'll answer some questions at the end. So we always like to start presentations with a quick safety moment. At ALS, one of our core values is that safety is a priority. We have an obligation to keep our families, friends, employees, customers, vendors, and neighbors safe. So at ALS, we have developed some life-saving rules, and these were developed from a review of major incidents or high potential incidents, near misses that occurred in ALS and in the industry in general. Today's life-saving rule that I want to talk about is regarding remote work. When working remotely or alone, always remember to notify someone that you will be working remotely, have and follow a plan for the work to be carried out, have a regular call-in or check-in schedule, be aware of local weather conditions and wildlife if you're in the field, and also be aware of emergency service response time. You might be in a remote station and so you're protected from wildlife and the elements, but if something else happens, like a medical emergency, is it going to take an hour or a half a day before someone can get to you? Okay, so first we'll just go over a brief introduction about ICMS instruments in general. For some of you who may know the term ICMS but don't know what it actually stands for, the term ICMS is an acronym for inductively coupled plasma mass spectrometry, and is used to describe a family of instruments that use a plasma, typically an argon plasma, as an ion source and a mass spectrometer as the analyzer. In environmental testing, there are two main types of ICPMS, and those are magnetic sector and quadrupole MSs. Magnetic sector ICPMS instruments are often referred to as high resolution ICPMSs due to their ability to separate or resolve analyte signals from interfering signals. So they usually offer, or traditionally have offered, the lowest detection limits that you can get. This is accomplished through the use of a fairly large electromagnet. The magnet alone weighs about 50 kilograms and is the size of carry-on a piece of carry-on luggage in an airplane when we used to be able to fly on airplanes. However, there are a fair bit of trade-offs with magnetic sector ICPMS that may not be offset by the benefits of the increased sensitivity. First, due to the size of the magnet and the need for multiple vacuum chambers and pumps, the whole instrument is roughly the size of 2 household fridges, so it takes up quite a lot of space in the lab. Second, relative to quadrupole ICMSs, the magnetic sector MSs are fairly complex in their operation. Not only do you have to tune the instrument so to focus your ion source, but you also need to tune the magnet in order to make sure you're looking at the right spot, because if the magnet's not tuned properly, you can what you think is a peak at, say, mass 40 is actually a peak of something else. So it's very important that the magnet is tuned properly and you're looking at the right thing. It will vary slightly by manufacturer, but magnetic sector MSs can have up to 2 vacuum chamber, a couple flight tubes, 2 sets of quadrupoles that are used kind of to focus the ion stream, and up to 6 vacuum pumps, like 2 rough pumps and 4 turbo pumps. So all of those have to be working in unison in order for you to get those ultra low detection limits. And one of the other challenges with the high magnetic sector MS is that because the magnet is so big, if the ambient temperature in the room changes by a few degrees Celsius, we've noticed that your mass peak can shift by a couple, what it looks like a couple mass units away. So you have to retune the magnet in order before you can do any analysis. And then lastly, the magnetic sector MSs are very expensive. They're about 3 to 5 times the cost of a quadrupole instrument. So all these things, if you need the ultra low detection limits, and they're great, but if you're just doing a few samples with at the ultra low level, but you have hundreds or thousands of samples to run, that might not be the best option for you. Quadrupole MS instruments are much more cheaper, compact, and simpler to operate over magnetic center. Unlike the magnet in a sector MS that takes 2 to 3 people to lift, the quadrupole assembly can be held in one hand and is about the size of a 750 ml bottle of wine. The main issue with quadrupole instruments is that, at least initially when they were first developed, they couldn't deal with interferences very well. But the introduction of collision and reaction cell technology, or CRC technology, has greatly improved the interference removal capabilities for quadrupole instruments, such that they're now the industry standard for multi-element analysis in environmental testing. However, one interference that cannot be removed by the collision cell ICPMS is from doubly charged ions, which we will talk about in an example later when we talk about low-level arsenic analysis. So to just go over kind of the sample flow, how you go from having a liquid in a tube to getting a number out of the instrument. So the liquid sample is turned into an aerosol and then is injected into the argon plasma. The plasma turns the sample into a stream of charged ions, because due to the high amount of energy in the plasma. The argon plasma is about 5,700 degrees Celsius, which is the same temperature as the surface of the sun. At this temperature, all molecules and complexes are broken down into their constituent elements, and those elements will have one electron removed, creating a +1 charge. After the plasma is the interface region of the instrument, where the plasma passes through a set of sampling cones or interface cones. And then the ion stream is focused by a lens stack and then enters the analyzer chamber of the instrument. And in the analyzer chamber, you'll first have typically the collision reaction cell, and then you'll have the quadruples and the detector. And all that is kept under high vacuum, about 10 to the -4 pascals. And then, so when the ions enter the collision reaction cell, they'll either interact with typically hydrogen or helium. And hydrogen will react with any interfering polyatomic ions, changing their mass, so they'll be rejected by the mass filter or the quadruple. And if it's helium in the cell, it removes via interferences via kinetic energy discrimination. Basically, the polyatomic interfering ions are a bigger radius, so they'll end up hitting the helium gas more often, and they'll lose their energy and don't have enough to get out of the cell and into the quadruple region. For low masses, low elements like lithium, beryllium, and boron, where you don't really have any polyatomic interferences, because if you add anything to those analytes, it's not going to be the mass, the low mass anymore. So you don't usually run a cell gas when you're analyzing those three analytes. As the ions exit the collision reaction cell, they're then filtered by mass charge ratio by the quadruple. Knowing that the ions exiting the CRC will have a +1 charge, the instruments can filter the ions like this. The filter ions then enter the detector, where it will collide with a metal plate in the detector, which is also called an electron multiplier. And this collision displaces an electron which hits another plate and then displaces more electrons via secondary emission. And then the process is repeated until you get until you amplify the electrical signal and measure it. And then you have software to convert the electrical signal into a number that you can use, that you can apply to a calibration curve. All right, so this is just a picture of the interface region. So you have the torch here, the argon plasma. This coil is the radio frequency coil, and it operates about 25 megahertz, and that is what excites the argon gas to form the plasma. And then if you can just kind of see in the middle here, this is a glass tube that will inject your aerosol sample into the heart of the ICP flame. So that's the hottest part. That's where it'll be 5,700 degrees. And then it will, it's actually in direct, the plasma is actually in direct contact with this nickel copper cone. And the reason it doesn't melt is because the cone is water cooled, along with the RF coil here. So, and then there's a cooling gas that kind of shields everything else from melting in the instrument. So as you might imagine, this the instrument requires a lot of argon gas. It's flowing at about 15 liters a minute. And to put that in perspective, so your standard T-size cylinder that's like 9 inches wide and 55 inches tall, charged was about 3,000 psi. That would only give you about 6 hours of runtime. So you you need a bulk source of argon in order to run these instruments. Okay. So the common question is that we often get is like, how do we know the ions created in the plasma are just +1 and not +2 or some other valence? And that's basically based on the ionization potentials. Most elements, the first ionization energy is below 10 electron volts, and so the plasma can strip that first electron away pretty regularly. But in order to strip the second electron away, you have to look at the second ionization potential, and those you can see are much higher. Lithium is off the scale on this chart, and it's at 75.6 electron volts. So basically, no matter what energy source you use, you're not going to get a +2 lithium ion. Let's see. Okay, yeah, that's pretty much for this one. And then, so this chart is kind of shows you like how much of each analyte is ionized in the argon plasma. So it creates, that will usually create a +1 charge. So the majority of ion elements are between 80 and 100% ionized in the argon plasma. The elements that are less than 50% ionized have a first ionization potentials above 8.9 electron volts, and those ones are arsenic, beryllium, cadmium, phosphorus, selenium, sulfur, tellurium, and zinc. Seeing that the argon plasma can't completely ionize all elements with an ionization potential above 8.9 electron volts, and knowing that the second ionization potentials are usually greater than 10 electron volts, we can be fairly confident that the majority of ions have a +1 charge. But that being said, you can't assume that there are no double charged ions in the plasma or formed by the plasma. So now that we have a basic understanding of current collision cell ICMS instruments, we can talk about what changes and improvements have been made with the triple quad ICMS. A little side note is that triple quad ICMS are often just referred to as triple quad, but there are different notations used out there. ICPMS MS or QQQ-MS, or triple quad, seems to be the most common, but it could be something else. And then second is that when you're looking at schematics of like how ions flow through the instrument, you'll often see them say, oh, Q1 is going to be in front of the cell, Q2 is after the cell, but it never lists Q3. And the Q3 usually refers to the collision reaction cell. Although the cell is more kind of an ion guide, it doesn't really act as like a mass filter like the other two quadrupoles. So it depends on how you defined the quadrupole. Regardless of that, as I kind of alluded to, in general, the configuration will be you'll have your interface region, which is the plasma cones and your lens stack. Then that will go into your first set of quadrupoles, and then that will go. The ions will then go into your collision reaction cell that may have any reaction or collision gas in it, and then your final set of quads just before the detector to focus or to filter out your product ions. And having the set of quadrupoles in front of the reaction cell allows the instrument to control which ions enter it, and thus enabling more reactive gases such as ammonia and oxygen. Most triple quads will operate in three different modes, and the first mode is kind of pointless for this one, is that you can turn the first set of quads off and act in single quad mode. So it'll be the first set of quads will allow all the ions to enter in the cell, which is kind of like a regular collision reaction cell. So it's not very useful in this with this instrument. The second is the MS en masse mode. And in this mode, your Q1 and Q2 are set to the same mass. And then the interfering ions will react with the gas in the cell and form a higher mass product, which is then rejected by Q2. And then there is an MS mass shift mode, where Q1 and Q2 are set to different mass. So your Q1 will filter out all your target ions will react with the cell, forming a higher mass product, and then the target ion is mass shifted. So arsenic will be an example of this. And the higher mass is acquired by Q2, and then everything, your interfering ions that didn't react with the gas stayed at the mass at Q1 was set to, but then are rejected by Q2. And then, so the lower detection limits available on the triple quad are mainly achieved through improved signal to noise ratio. And then, as it says at the bottom here, and by using these modes, you can effectively remove interference from doubly charged ions. So the next few slides will cover a couple examples of how the en masse and mass shift modes work on the triple quad. So the first example is using MS en masse mode and oxygen cell gas to remove molybdenum interference on cadmium. Cadmium is in the same group as mercury on the periodic table and is on the World Health Organization's list of 10 chemicals of major public health concern. As such, regulatory or permit limits are often very low for cadmium. Cadmium analysis requires detection limits in the nanogram per liter or parts per trillion range for most environmental monitoring projects. However, ultratrace cadmium analysis has always been challenging due to polyatomic interference from molybdenum in the form of molybdenum oxide. Cadmium has 8 different mass isotopes, and all of them except for cadmium-111 have an isobaric interference from other elements. An isobaric interference is when an interfering element has an isotope of the same mass as the target element. Standard collision cell ICMS cannot separate 2 monoatomic isotopes with the same mass to charge ratio. For example, the 2 major isotopes for cadmium are actually cadmium-112 at 24% abundance and cadmium-114 at 29% abundance. But both of those are overlapped by isotopes of tin. So if you had any tin in your sample, those 2 masses would show a high bias. Using helium in a collision cell removes most of the polyatomic interference from cadmium-111, But as we'll see on the next slide, the risk of false positives due to polyatomic molybdenum oxide is still significant, even with relatively low molybdenum concentrations. So the image below shows how the MS-MS on mass mode removes polyatomic interference from cadmium. First, Q1 filters all ions except for those with a mass to charge ratio of 111. This prevents molybdenum 95 from entering the cell and forming molybdenum oxide, which is what would happen if you were to use oxygen in a standard collision cell instrument that didn't have a set of quads in front of the cell. Second, the molybdenum oxide that was formed in the plasma will react with oxygen in the cells and be shifted to mass 127. So you can see in the bottom there in red, the molybdenum oxide will react with oxygen to form molybdenum dioxide. And then since cadmium doesn't react with the oxygen, at least not at a detectable rate, it will pass through the cell and enter Q2, which is also set to acquire ions with mass 111. So this chart illustrates the impact of molybdenum interference on cadmium, how improvements in ICMs technology has reduced the interference over time. The amount of observed interference is directly proportional to the concentration of molybdenum. So if 100 microgram per liter molybdenum interference causes a 60 nanogram per liter interference on cadmium, we would expect the interference from 50 micrograms per liter molybdenum to be about 30 nanograms per liter in cadmium. Obviously, the way to reduce the interference is to reduce the molybdenum concentration, and that's usually done by diluting. You could do it by solid phase extraction as well, but then you have to involve more complicated sample preparation. One of the downsides to dilutions, if the dilution required to reduce the molybdenum concentration is so great, you may end up diluting out the cadmium signal or other analytes of interest. So you might end up reporting false negatives for other analytes. So in this chart on the far left is the observed cadmium background in a 2% blank nitric acid solution. So that's the dark blue bar, and then the cadmium, the observed cadmium concentration with 100 micrograms per liter molybdenum standard. And this is on either a regular non-CHC ICMS without any collision gas, or this is what you would expect for the first generation of quadruple MSs that didn't have a collision cell, or if the collision cell was turned off on modern ICMSs. So in this, we're showing that 100 micrograms per liter molybdenum gives you about 60 nanograms per liter cadmium false positive hit. The middle chart shows the same two matrices acquired using helium as a collision gas. This is the most common acquisition method used today. The use of a collision gas prevents most of the polyatomic molybdenum oxide from exiting the collision cell and reaching the detector. The false positive signal using helium gas is about 3 times lower than the signal without helium, but it's still above most detection limits for cadmium and water. So here it's about 15 nanograms per liter. Finally, on the far right, we see how effective the triple quad using oxygen as a reaction gas can completely remove the molybdenum interference by shifting it to a different mass. Keep in mind there is still a limit to the amount of molybdenum oxide that can be removed. At some concentration, the interference will become a concern again, but this concentration will be much higher compared to standard collision cell ICPMS. In this example, 100 micrograms per liter molybdenum is producing about half a nanogram false cadmium signal. So depending on reported detection limits, the concentration of molybdenum required to produce a false positive will be well over 500 micrograms per liter, and most environmental samples, typically you don't have a high concentration of molybdenum. One of the reasons the molybdenum oxide interference isn't always removed is also due to the speed of reaction in the cell. So you have to start considering reaction kinetics, how fast, given the speed the ions are moving through the cell, it might not have enough time to react with all the molybdenum oxide to shift it. So some might still pass through and enter the Q2. And then the only way to avoid that is either to increase the length of the cell so it has more time to react, or somehow slow the ions down in the cell, but still have them enough energy for them to enter Q2. The next example we'll look at is using the MS mass shift mode to address interferences on arsenic. Arsenic is another element on the World Health Organization's list of 10 chemicals of major public health concern. So again, regulators often require very low detection limits. And just if you're curious, other elements on that list are mercury, lead, and fluorine. Arsenic is one of the more challenging elements to analyze for, mainly because it's poorly ionized in the argon plasma with a relatively high first ionization potential of 9.79 electron volts. So it only is about 20% ionized in the argon plasma. It usually suffers from interferences from the plasma itself, primarily in the form of the presence of argon chloride, which can form from either chloride in your sample or from hydrochloric acid that is used in your standards. Unlike cadmium at mass 111, at mass 75, arsenic can have interference from doubly charged rare earth elements. The polyatomic interference poses the biggest concern for low-level arsenic analysis. The fact that arsenic is only 20% ionized is not ideal, but there is still more than enough ions to work with. Fortunately, most of the polyatomic challenges have been addressed with the introduction of collision cell ICMS using helium as a collision gas. However, the collision reaction cell in helium mode cannot remove interference from monoatomic doubly charged rare earth elements, so we must rely on either usually correction equations, but using correction equations is not ideal because they can be complex or difficult to derive. There may be different equations depending on the analytical method being used, and since you're manipulating the data, there is a risk of over or under correcting. So you really have to make sure that if you are using a correction equation that it is correcting properly. So when we're talking about rare earth elements with respect to arsenic, we are referring to neodymium and samarium. Both have several stable, extremely long-lived isotopes, but the only ones that are concerned for arsenic are the two at mass 150. So that's double the mass of arsenics. Neodymiums and samarium are often found in plant and soil samples. The amount of interference will depend on how effective the digestion procedure is at extracting the metals into solution. into solution. The interference from neodymium and samarium in the marine waters is rarely rarely observed. Yeah, so it's not so for waters analysis, we don't really have to worry about double charge from these two rare earths, but on in plants and soil samples, it's you do need to monitor it and make sure it's not there. Um, And the reason is we have to worry about these two is that neodymium and samarium have relatively low second ionization potentials around 11 electron volts, and the first ionization potential of arsenic is around 10. So, um, so only about you can see at the table below. Arsenic, the first ionization potential 9.79, that's only about 20% ionized. Neodymium and samarium, they're well below that at 5, so those are 100% ionized. And we would expect about 1% of that to be double charged neodymium and samarium. As mentioned previously, the main difference between on mass and mass shift modes is that Q1 and Q2 are set to different masses in mass shift mode, and the reactive gas in the collision reactor cell reacts with the target element instead of the interfering ion. In the illustration below, Q1 filters all ions except those with mass charge ratio of 75. So if you have double charged neodymium and samarium 150, so it'll be 150 over 2, so it'll be a mass charge ratio of 75, same as arsenic. So yeah, in the installation below, filters Q1 filters all ions except those with mass charge 75 and allows them to enter the collision reactor cell. In the cell, the arsenic will react with oxygen to form an oxide and shift to mass 91. The interfering polyatomic and doubly charged ions do not react and remain at mass 75. Q2 is then set to mass 91, filters all the remaining interferences still at mass 75, and allows the mass shifted analyte to reach the detector. This is only possible because Q1 has prevented any mass charged ions of 91 from entering the cell in the first place. So, for example, zirconium. So zirconium wouldn't react with the oxygen, so it would also be at mass 91 after the cell. So you need to prevent that from entering the cell in the first place. So that does it for our examples. Some of the other challenges for ultra-trace metals analysis, aside from instrumental interference, the next biggest factor that can affect data quality is contamination. As instrument sensitivity improves and the need for lower detection limits increases, it becomes more and more important to monitor and control all potential sources of contamination from sample collection, preservation, preparation, and final analysis. In fact, controlling all possible vectors of contamination is the biggest challenge to achieving ultra-low detection levels. So the example below, gloves are often overlooked as a source of contamination as they are primarily meant to protect the person collecting or handling the sample. But for ultra-trace metals analysis, protection for the sample must also be considered. The chart below compares the two most common glove materials, vinyl and nitrile gloves, from a few different manufacturers. So clearly, the nitrile glove material poses a much greater risk of contamination over vinyl gloves, but even amongst the vinyl gloves, some brands are better than others. This has become even more pertinent with the current pandemic causing worldwide shortages of PPE. So getting a consistent supply of PPE has been quite difficult for labs because they're being used up by the health industry. So there were periods last summer where we were getting a different brand of gloves every other week, and each one of those brands had to be tested for cleanliness before they would be allowed to be used in the lab. Keep in mind that this chart is the absolute worst case scenario where the glove comes into direct contact with an acidified sample. We normally wouldn't expect this level of contamination from just handling the sample bottle and not coming into contact. So this would, I guess it would be closest would be you got a drop on your glove and that drop somehow landed inside your bottle. So it's fairly low risk, but it is something you just need to be aware of. And then, and the chart is also showing the sum of all the analytes, but typically the major contributors are calcium, sodium, potassium, and zinc. And then we at ALS, we go through the same type of process to validate all all of our sampling supplies from the bottles, gloves, and preservatives. And then in the lab equipment like test tubes and reagents, dispensers, pipette tips, etc., that could potentially come in contact with the sample. So now that we've gone over the ICMS, the triple quad, and how it works, the next question you probably have is what sample types can ALS analyze? Currently, we offer an ultra-trace metals packages for dissolved and total metals in pristine or low-level waters that are and are currently developing packages for seawater and biota or tissue samples. For dissolved metal samples, or for dissolved metals, samples should be field filtered through a 0.45 micron membrane filter and sent to the lab unpreserved. Field filtration became a requirement for all regulatory work in BC in 2019. It is highly recommended that a field blank is also submitted to A&M data interpretation. So if you send a set of samples in and all of them except a couple of them have a zinc hit, and then we could confirm it, but then if you also sent the field blank and we saw that there was zinc in the field blank as well, then we might think, okay, maybe it was this field contamination and it's not from whatever your water source is from. For total metal samples, samples should be unfiltered and have less than 1 NTU turbidity. And an NTU, if you didn't know, stands for nepheliometric turbidity units. We do recommend that clients recommend to clients that when samples are submitted for total metals, that they do also be analyzed for turbidity. If a sample is greater than 1 NTU, then the results may be biased low and cannot be considered for total metals for regulatory purposes. ALS currently does not offer a digested total metals package for the triple quad because the digestion procedure often leads to an increased background and that results in higher detection limits, in which case analysis by regular collision cell ICMs may be a better option. The increased background between undigested and digested samples is generally small, but when detection limits are in the mid to low nanogram per liter range, it becomes significant. For example, the aluminum background in a typical digestion blank is about 0.8 micrograms per liter, which is fine, and it's not really a concern for routine waters where the detection limit is 3 micrograms per liter. But for ultra-trace, it's 4 times over our detection limit for the triple quad. So, your detection limit could still be lower than standard, but if there's other high analytes, then it just might working overall to be better to do it by regular collision cell than the triple quad. Regarding sample preservation, we do recommend that samples be preserved by the lab for both total and dissolved metals. This is to minimize the risk of contamination and to reduce the need to handle and ship hazardous preservation, so we don't have to ship you vials of acid into the field. It also helps to reduce the amount of plastic waste, again, because you don't need to have a separate plastic vial for your preservative. However, if a quick turnaround time is required, less than 48 hours, proofed acid preservative vials can be supplied for field preservations. Samples that are field preserved do not have to undergo the mandatory 16-hour equilibration period that lab preserved samples do. The equilibration period is to make sure that anything that had fallen out of the solution or absorbed to the side of the wall of the sample container has gone back into solution. And as I mentioned, we are aiming to have packages available for seawaters and tissue matrices later this year. So finally, here's a full list of detection limits currently being offered for total and dissolved metals in pristine waters. A few highlights would be cadmium at 2.5 nanograms per liter, about 50% lower than the routine 5 nanograms per liter detection limit. Arsenic at 10 nanograms per liter, about 10 times lower than the routine, and selenium at 25 nanograms per liter, about half of what routine currently offers. As Alex mentioned, May mentioned, this slide will be presented or sent out at the end, so you don't need to rush and write all these down. So all the triple quad analysis is done at the Vancouver Environmental Lab. The Environmental Lab in Vancouver is one of the leaders in terms of ICPMS analysis in the ALS network. It currently operates 6 collision cell ICPMS instruments for routine analysis in water, seawater, soils, and biota matrices. Vancouver is also the base for most of the specialty ICMS services offerings. In addition to the 6 routine instruments, Vancouver also has an HPLC ICMS instrument for arsenic and selenium speciation, as well as a GC-ICPMS that will eventually be used for analysis of tetraethyl lead in waters. So with this, with all the experience at the Vancouver lab, this made sense for us to put ALS's first triple quad in the Vancouver lab. If you like more information on sampling for triple quad analysis, quotes, or information on other ALS service, you can either contact your account manager if you're already working with ALS, or contact the Vancouver lab directly by emailing vancouverenviro@alsglobal.com, and that will be sent out to our client services team based in Vancouver. Or you could use one of the phone numbers to give us a call. So here's my contact information. If you have more specific technical questions regarding ICMS analysis, triple quad analysis, or just trace metals analysis in general, feel free to reach out to me directly. I would say that email is probably the best way to get a hold of me, as I'm often in and out of the lab all day, so I'm not always at my desk able to take phone calls. So to quickly summarize, ICMS is the instrument of choice for trace and ultra-trace level multi-element analysis in environmental samples. Triple quad ICPMS offers improved sensitivity for ultra-trace analysis through superior interference removal compared to current generation collision cell ICPMS. And when doing ultra-trace metals analysis, you need to consider all vectors for contamination and only use supplies that have been verified to be suitable for ultra-trace analysis. And then just at the bottom there, we did have an environment mail, which is kind of a newsletter that was published in August 2020, and that also covers, gives a little bit higher overview of some of the topics that we discussed today. And that about does it. Thank you for your time, and again, feel free to reach out to me if you have any further questions regarding triple quad or ICMS analysis.
Thanks, Richard. I'm going to open up the forum for questions now. If you can write out your questions using the Q&A function at the bottom of the toolbar of the webinar. Attendees can also see all submitted questions using this window. While I give everyone a few moments to type in their questions, I'll review some brief notes. This webinar presentation has been recorded. All participants of this webinar will receive a follow-up email once the recording is available to view. We also post our webinars on our ALS Global website and our ALS YouTube channel in the webinar playlist. I encourage everyone to find a wide range of video resources and past Webinar Wednesday presentations available there. Also, please follow our company page on LinkedIn as we post announcements and registration links to future webinars and other valuable resources and updates. We have a question from Lisa. She asks, how do you define your detection limit?
The detection limits are based on the matrix background. So we'll run say 10 method blanks, see what the background is, and then calculate the detection limits from there. So the general rule is it's like 3 times the standard deviation of your blanks plus the absolute value of your mean blank. So that's the general rule that we use for establishing detection limits.
She also asks, do you do it in 1 day or in 10 days?
And like do the blanks, well, we'll do the we'll typically run the blanks will be all run on 1 day, but then we'll also repeat it on other days so we have them over different calibrations. So we'll try and get more than one in calibration, but initially we'll just run 10 1 day, we might run 10 another day, and then another 10, so overall you'll have a bigger data set.
Okay. Jack asks, do you see the triple quad ICPMS replacing collision cell approaches in the future?
It could. The collisions or the regular collision cells are pretty good at for most analysis. It's really the only real benefit that the triple quad will give you is if you have a specific interference that you're trying to remove, and then, as I said, the triple quad can remove a double charge interference for some analytes, which the regular collision cell can't. So, but I would say that the regular collision cells were probably going to be the standard for quite some time until, yeah.
Okay. I don't see any more questions. I just want to thank everybody for attending today. Again, you can contact Richard for any questions. His contact details will be included in the follow-up email, along with the link to today's recording and I'll also link to that environmental he was talking about. I hope everybody enjoys the rest of their week. Thanks.
Thank you.